And in this talk, I'll present our recent work on semi-oblivious traffic engineering. So in order to meet various competing objectives, operators of wide area network use traffic engineering to steer traffic in desired ways. And a good traffic engineering system should be able to ensure high performance in terms of throughput and link utilization while being robust to failures. Traffic in these wide area networks often have different latency requirements. For instance, low latency requirement for customer-facing traffic or customer traffic, while more relaxed requirements for bulk and replication traffic. So a good traffic engineering system should be able to meet these, provide these guarantees as needed by the applications. And finally, it should be operationally simple so that it is easy to root cause and debug any issues that may arise in production. And traffic engineering systems should be able to achieve these competing objectives in the presence of various challenges. For instance, wide area network topologies evolve based on anticipated growth in demands. So this can lead to unstructured topologies, unlike data center topologies, and it can also lead to heterogeneous link capacities. Failures, such as a link going down or a misbehaving router, is quite common in such networks. And similarly, it is quite difficult to predict these demand matrices, demands in advance. So traffic engineering systems should be able to handle these unexpected failures or mispredictions. It should also take into account various device limitations. For instance, as we saw in the previous talk, that the number of flow rules that you can install on a router is bounded, so you want to take those constraints into account. And finally, updating the routing state in response to a change in demands can lead to significant overheads. So let's see some approaches to traffic engineering. So the traditional approach to traffic engineering relies on tuning link weights in distributed routing protocols, such as OSPF or ECMP, so that they compute a good set of forwarding paths. So for instance, by updating the weight of this link, an operator can route the traffic over this alternate path. So these approaches are simple to implement because they harness the capabilities of widely deployed conventional routing protocols. However, tuning link weights to actually achieve optimal performance is hard in practice. Also, these protocols do not work well when failures occur or during periods of reconvergence when link weights have been updated. So around 5 to 6 years ago, enabled by software-defined networking, or SDN in short, we started to see centralized approaches to traffic engineering. So with SDN, it gives us the global visibility and direct control over the network. So in principle, you can assume that you can think about deploying the optimal routing scheme at every moment in time. One such example would be to formulate routing problem as an optimization problem and say use an off-the-shelf LP optimizer to solve the corresponding multi-commodity flow problem. But note that it's not practical to actually achieve optimal performance using such an approach. And to understand why, note that to actually achieve optimal performance, you'll have to take the network snapshot quite frequently, solve the MCF problem, translate into the solution, and then install this routing scheme at a very high rate. And this is not possible due to various operational constraints. For instance, let's look at the time required to solve an MCF instance. So here on the x-axis, we have traffic matrices over the period of a week. And on the y-axis, we have time required to solve the corresponding MCF instance. And this is based on the topology and traffic matrices from a real production wide area network deployed at Facebook. So we find that it takes roughly 30 seconds to solve each MCF instance. And this kind of sets a lower bound on how quickly can you react to changes in demands. And more importantly, the solution of an MCF instance using an LP solver is not guaranteed to be similar to the solution that you got when you previously solved the MCF instance. So this means that you will need to update the routing state by changing the forwarding paths. And this leads to path churn. So again, for the same topology, we measured path churn over the period of a week, and we found that we would need to add or remove around 2,000 forwarding paths in each iteration. And these updates need to be performed in a consistent manner so as not to introduce any transient congestion or forwarding loops. So this imposes a significant overhead on the routers. So how did people actually build traffic engineering systems with such operational constraints? Well, let's take a step back and see what a traffic engineering system actually does. It has to perform two things. First is path selection, that is given a source and a destination, which set of forwarding paths should it use. And the second is what we call rate adaptation, is that given these multiple paths from a source to a destination, how should traffic be split across these multiple paths? And it turns out that path selection is a slow and expensive process because you might need to update many geo-distributed routers for a single path update. On the other hand, updating the splitting ratios is quite cheap and fast because you need to update these weights or the splitting ratios only at the, say, ingress router or only at the edge. So the key insight here is that we may change the forwarding paths very infrequently, but we can update the splitting ratios much more frequently. So since we are sort of committing to these paths once we have computed them for a really long time, then how should we compute these paths so that they can ensure good performance and robustness over a long period of time? So the main thesis of our work is that by cleverly constructing a static set of paths, we can achieve near optimal performance and very high levels of robustness. And for this, specifically, we highlight that the path selection algorithm for selecting these static set of paths should have the following 3 properties. First, it should select paths with low stretch to minimize latency. Second is that the path selected should have high diversity so that the traffic engineering system can be robust to failures. And the third is that the paths should be selected in a capacity-aware and globally optimized manner for good load balancing. So I'll explain what I mean by these 2 terms in the next couple of slides. So for capacity awareness, let's take this example of a very simple topology in which all the links are 100 Gbps except this dashed link from G to E, which is a low capacity 10 Gbps link. And let's say we are using something like shortest path first routing, which doesn't look at the capacity in this case. And let's say E is the destination, and we have 3 sources trying to send 10 Gbps traffic each to this node E. Now, since the shortest path scheme is not capacity aware, all the shortest paths end up taking the low capacity link, leading to congestion in the network, even though there is spare capacity. So that's why we need the path selection algorithm to be capacity aware. Next, let's modify the same topology, but let's make all the links with homogeneous capacities. And let's use a traffic engineering system which is capacity aware, which is called constrained shortest path first, or CSPF. So what happens with CSPF is that as demands come in, it tries to find the shortest path with sufficient capacity to route that demand. So let's say all the links are 100 Gbps each. E is the destination. A wants to send traffic, and the demand is 100 Gbps, so it will select the shortest path through G. Now, when B wants to send traffic, it will have to take this other detour because the link from G to E is saturated. And finally, when C wants to send traffic, it will have to take this really long detour. Now, this is clearly suboptimal because we didn't consider all the source and destinations together. Instead, if we had done that, we could have come up with a much better set of paths. So it turns out that most commonly used path selection algorithms often do not meet the criteria for good path selection. For example, those based on shortest paths can provide us low latency, but they are often not diverse enough to provide robustness, or they do not provide good load balancing properties. We can achieve good load balancing by doing something like solving the multi-commodity flow problem, and MCF will give us good load balancing, but often the paths computed by MCF are brittle, or they do not provide us good latency. So in the past, people have looked at oblivious routing schemes, as we saw in the previous talk. So let's look at oblivious in a little bit more detail. Well, I won't go into explaining the algorithm itself, but I just want to highlight the key properties of oblivious routing that may make it a good candidate for a path selection algorithm. So specifically, I'm referring to this algorithm that Harry had proposed in 2008. And the algorithm works by generating a distribution over routing trees called a randomized routing tree. And so yeah, here we see the distribution over routing trees. And each routing tree is computed using an approximation algorithm that guarantees that the path lengths in the routing tree are close to the shortest paths that you will get in the actual graph. So this gives you low latency. And this is an iterative algorithm. So in each iteration, the weight of each link is adjusted based on how much the link has been used in the previous set of routing trees. So this ensures that when you look at the final ensemble of routing trees, no single link will be congested. So that will give us good load balancing. And again, since we are avoiding using the same link multiple times, it will also give us good diversity. So ultimately, we find that oblivious routing meets all the criteria for good path selection algorithm. Further, it has also been shown to be log-n competitive. So what this means in this context is, no matter what demands arise in practice, the maximum link utilization or congestion that you'll see with oblivious routing is guaranteed to be within log-n factor of the optimal MCF. Now, this is a very powerful theoretical result, but in practice, this still means that we need to over-provision our network by a significant amount. So the question is, can we do better? And the short answer is yes, and let's see how. So for this, Smore proposes using Oblivious routing to compute the static set of forwarding paths. And then, based on demands that arise in practice, it dynamically updates the splitting ratios at the end host using an LP optimizer. So this approach of semi-oblivious routing has been shown to be not significantly better than oblivious routing in the worst case. But what we are interested here is not the worst case, and these worst case scenarios do not typically arise in practice. So the question we ask is, how well does the semi-oblivious routing work in practice? So to evaluate semi-oblivious routing, we took the data from Facebook's wide area network, which consists of many large data centers and points of presence spread across the globe. And traffic on this network has both latency-sensitive traffic as well as traffic with more relaxed requirements. So we took accurate snapshot of the topology and the traffic matrices for over a month, and we performed high-fidelity simulations to measure the performance and robustness characteristics. So let's look at performance first. So on the x-axis, we have time. First, we compared many different traffic engineering systems, and for each traffic engineering system, we have a time series here, and on the y-axis, we have different metrics such as throughput, congestion drop, and max link utilization. Let's just focus on the maximum link utilization, and let's start with optimal. So what we saw was that with optimal, the maximum link utilization varies between 40 to 65%, following a diurnal pattern, while it is able to achieve 100% throughput. And without going into the details of all these other schemes, I just want to highlight that Smore was performed much better compared to others, and the maximum link utilization with Smore was within 16% of the optimal MCF. Next, we performed some experiments to measure the robustness of these different systems. So what we did was that for each traffic matrix, we would fail one link in the traffic matrix, in the topology, and we would allow the traffic engineering systems to react to these failures if they can, and then we measure the performance again. So let's look at optimal again. So what happened was that optimal was still able to maintain 100% throughput while it was able to reroute around most failures, but at the cost of increased link utilization. And we found the same situation with every other traffic engineering system as well. And Smore was again able to achieve almost 100% throughput with maximum link utilization close to optimal. So for this particular topology and for this particular setting, we saw that Smore is providing near optimal performance and robustness. Note that these experiments were done with a path budget of 4 to simulate some operational constraints. So what this means is that for any traffic engineering system, we bounded the maximum number of paths that you could use between a source and destination to be up to 4, except optimal. Optimal could use any unbounded number of paths. So when we relax these operational constraints, for example, when we allow these traffic engineering systems to use more paths, we found that other schemes, such as those based on case shortest paths and case shortest paths with dynamic rate adaptation, are also able to get near optimal performance, but at the cost of increased number of paths. But Smore was able to achieve the same level of performance with much less number of paths. So the paper talks about other operational details in much more detail. So I'd encourage you to have a look at that. So next, the natural question to ask is whether these performance and robustness characteristics of Smore are specific to this particular topology and traffic matrix, or do they generalize over a large number of settings? So for this, we performed large-scale simulations using topologies from Internet Topology Zoo dataset, and we generated a large number of traffic matrices using the gravity model. And we found that while there is some variance across all these topologies and traffic matrices, overall, Smore continues to have good performance and robustness. For instance, in this graph on the left, we have normalized capacity on the x-axis, and where we define capacity as the factor by which you could scale up a traffic matrix before we see that any link is saturated. And these values are normalized with respect to the optimal MCF, and we found that Smore, again, performs close to near optimal overall. Similarly, for robustness, we measured the probability of achieving different levels of throughput SLO, and we again found Smore to be quite robust. So to summarize, we found that path selection plays a critical role in the performance and robustness of traffic engineering systems, and Smore, which combines oblivious routing for path selection and dynamic rate adaptation, is able to meet these competing objectives over a wide range of scenarios. And finally, we have made all our code open source on GitHub, so feel free to check it out. And this talk was based on the following papers here. And with that, I'm happy to take any questions.
Is there time for a few quick questions?
So you showed that semi-oblivious routing does very well in practice. So I was wondering, did you ever try to just run vanilla oblivious routing? How does that do in practice?
Oh, yeah. So here we have this. So this is the vanilla oblivious routing. So it is able to achieve 100% throughput, but as you can see, the maximum link utilization is slightly above, like maybe say 1.5 times what you'd see with optimal for this particular topology and traffic matrices. Again, for robustness, for when we generalize, when we can look at the experiments over this large set of scenarios, Oblivious was pretty good, but not like as good as if you had the information about the demand when you are running your traffic engineering system. But it did have very good robustness properties.
So in the talk, you mentioned two pieces of SMORE. One is the path selection, which is Oblivious, and the second is the flow allocation optimization function. If I remember correctly, flow allocation is minimize the maximum link utilization.
Right.
And I want to understand which part of these two pieces are contributing the most in your results.
So as you can see, so this is the direct difference between what you will get with vanilla Oblivious and with SMORE. So with vanilla Oblivious routing, as I mentioned, we can get the all the three properties of path selection, that is good load balancing guarantees, good diversity to handle failures, and low latency. So things like low latency and diversity always come from the path selection, but it is the runtime optimization that can lead to this difference in performance.
In other words, if I use Oblivious and use FFC's optimization, for example, or maximize bandwidth, where would that be? What would be the gains?
Right, that's an interesting question, but if you look at FFC's LP optimization, it's not optimizing for maximum congestion, it's optimizing for maximum throughput, right? So, so in our metrics, for instance, at least for this particular workload, we are always able to satisfy 100% throughput, so we will not see any difference here. But since FFC doesn't optimize for maximum link utilization, we will probably see the green line somewhere up here. But in that case, the black line, the throughput will be at 1, but the green line will probably be somewhere higher.
Yeah. Was it the last question? Yeah, because you mentioned FFC and I represented it after support. I want to ask, so for this figure, because FFC will have some throughput loss for the robustness. So I just wondering, under what kind of setup you did this experiment? So how many link failures are you going to prevent?
So this experiment is with FFC optimized for k equals 1, that is handling single link failures. And as you mentioned, it will have some throughput loss. So that's what we see in this case, that the black line is slightly below 1 because it was not able to completely handle the traffic for this particular workload.
Can you go down to the next slide? Next. The barcode. Yeah, here. So I want to answer. So FFC does suggest a way to select the path, right? So it needs the link or link disjoint path selection.
Yes.
Are you using that kind of
Yes. We are using S-disjoint path selection for FFC here. Yes, but not here. But like so in the previous thing, you would have seen that star because we are not implementing the full FFC. We optimized FFC for single failures in the data path, and we didn't handle control plane failures because FFC, I think, handles control plane as well. So that's why this is not accurately what you have in the paper. Yeah.
Great. So let's thank Praveen again.